we're going to begin our module on graph theory. Now, when you hear the word graph, you probably think about something like this. Okay, so these types of graphs are a representation of the solutions of an algebraic equation. And while they are graphs, they are not the type of graphs we explore in graph theory. Those types of graphs will look like this. They're basically going to be dots and lines. Now, graph theory started back in about the 18th century, and the way the story goes, it originated in a town called Königsberg. Now, in this town, as represented by this idealized map, what was going on is that there were 7 bridges that ended up connecting 4 land masses. Okay, so the bridges are in red right here, but there's a bridge here, here, and here. So there's 1, 2, 3, 4, 5, 6, and 7. So then the 4 land masses would be kind of this upper region, this island, this lower region, and then this region right here. And then if you can imagine, this was the Pragal River. This kind of just kept going on forever, separating out these pieces. So the townspeople of Königsberg would wonder if it was possible to start on one of these land masses and cross each of the bridges in their town once and only once. And this became a popular problem that they would discuss, at parties or sitting around in their local tavern or whatever. Now, these townspeople did not think it was possible. They didn't think it was possible for them to start at one of the land masses, cross all the bridges once and only once, and get back to where they started. But they couldn't prove it. They just didn't think that it was possible to do it. So eventually, these townspeople's problem reached a Swiss mathematician by the last name of Euler. Now, it looks like Euler, but his name is actually pronounced Euler. Okay, so Euler got word of what these townspeople were wondering, and he actually found this to be a pretty fascinating problem. He wanted to see if he could prove it to these people, whether or not it was possible or was not. And because of his exploration of this town and these bridges, this led to the birth of graph theory. Now we're going to come back and revisit this problem in a little bit, but first we need to cover some vocab relating to this discipline so that way we have consistent language. Now with that being said, not all textbooks and authors talk about graph theory consistently and define the various aspects of graph theory consistently. So just be careful if you're ever using an outside resource or perhaps going on the internet or talking to somebody who learned graph theory in another class. So maybe they took discrete mathematics and they learned graph theory there. Their textbook might have talked about it a little bit differently. Okay, so I had said graph theory is going to involve problems that look like this, dots and lines. The dots, are more formally called a vertex. Some textbooks may call this a node. Okay, we're going to call it a vertex. And then the line segments are going to be known as the edges. Now there's going to be some things that are going to be consistent, maybe with what you learned in a geometry course, and other things that are not going to be consistent. So one of the things is for the edges, while I put the line segments in quotes, those segments actually might be curved. So down here on this example, you can see that these connections of these vertices have curves to them, so they don't have to be straight. So instead of saying our graph had dots and lines, we're going to say that they have vertices and edges. Now, edges crossing does not generate a new vertex. So for instance, like right here on this example, this is not a new vertex right here. If you wanted it to be a vertex, we would have to put a pronounced dot there, and then typically we would label those vertices with capital letters too, just to make it very clear where the vertices are. Moving forward, we sometimes just put the big old dot there and omit the capital letters, depending on the application that we're looking at. Now the vertex set is going to be the set of vertices of a graph. So in this example over here, the vertex set is going to be A, B, C, D, E, and F. The edge list is going to be the list of all the edges of the graph. Now when we go to list an edge, we list an edge with its starting and ending vertex. And like in geometry, the order doesn't matter. So for instance, this edge right here, I could call that edge AB, or I could call it BA. Okay, it would be the same no matter what. So that grabs this edge. This edge right here, I'm going to call that edge AD. So this edge right here would be maybe DE. This edge right here, BE. This edge right here, BC. This edge goes from C to D. And this edge also goes from C to D. Okay, so any one of these edges you could have flip-flopped the two capital letters and it would have been referencing that same edge. Now for this edge right here, this edge starts at B and it ends at B. So that edge is called BB. That's actually a very special type of edge that's called a loop. So let's come down here. So a loop is an edge that starts and ends at the same vertex. Okay, so then maybe let's draw an arrow to it. Okay, so what's going on here is that we can call that edge BB, or we could all call it loop BB. So then now we can formally define a graph, which is the item that we explore in graph theory. A graph is a structure consisting of a set of objects, which is called the vertex set, and a list describing how pairs of objects are related called the edge set. Now this very simple idea of just having a set of objects and a set that describes how those objects are related actually has widespread applications. And graph theory is one of the kind of like the booming areas of mathematics. It's being used a lot more to describe all sorts of things that we might not have initially thought, hey, that actually can be modeled by graph theory. So it's used for routing goods from various locations. It's used in social networking theory to talk about how maybe people are related to each other. It can be used in biology to describe maybe migration patterns. And it can be used to, for instance, in interior design and in designing traffic flow patterns. Okay, so this simple idea has a lot of widespread applications. Something else that's going on in this graph is this isolated vertex. So this will be a vertex that has no edge connected to it. So here's an example of an isolated vertex. Okay, it's just sitting by itself. It doesn't have an edge connected to it, but it is considered to be part of this graph structure. Now another thing that we look for when we're looking at graphs is whether or not things are next to each other. So we can look at adjacent vertices or we can look at adjacent edges. So adjacent vertices are going to be vertices that are joined by a edge. So as an example, A and D are adjacent. Now I could say adjacent vertices, but the vertices is actually kind of implied just because of the elements I'm talking about, because A and D are vertices themselves. So A and D are adjacent because there is an edge connecting them. How about a non-example? A and, I don't know, how about E are not adjacent. Okay, there is not a direct edge connecting A to E. Okay, there is a way to get from A to E, and we're going to talk about that in a little bit, but these two vertices are not considered to be adjacent to each other. Now we can also look at adjacent edges. So adjacent edges are going to be two edges that share a common vertex. So again, as an example, how about BE and, I don't know, ED are adjacent. And again, I could have said are adjacent edges, but the edges is kind of implied because of the elements I'm talking about. It is easy to see when you state them whether or not two edges are adjacent because you have to cite their vertices, so you can see who that common vertex is. So these two edges are adjacent because their common vertex is E. That's not so easy to see for adjacent vertices because you just cite the letter. So in order to be able to determine if two vertices are adjacent, you would need to know your edge list or have the picture in front of you so you could actually see what the graph looked like. So maybe as a non-example, BE and AD are not adjacent. Okay, so BE is right here, AD is right here. They don't share a common vertex. So them, remember, this is not like an intersection point right here. They don't hit each other. So that being like, it's not like a common element that they share. So these two edges don't share a common vertex and therefore are not adjacent.